For decades, the most reliable prediction in tech was this: every 2 years, the number of transistors in a chip doubles. More transistors, more power, more speed. Gordon Moore called it back in 1965, and the industry basically built its entire roadmap around it. But we're running into a wall. Not a metaphorical one, a physical one, and the closer we get to it, the more expensive and absurd the process of shrinking transistor becomes. Right now, the most advanced chips are built on so-called 2-nanometer process nodes. To put that into perspective, a strand of human DNA is about 2.5 nanometers wide. We are literally etching circuits at the scale of biology, and yet it gets harder to push forward with every generation. A technology called direct self-assembly, though, or DSA for short, has been quietly developing in research labs for over a decade. Intel is now betting its future on combining this with next-generation lithography, and if it works, it could genuinely shift the balance of power in one of the most strategically important industries on Earth. Now, here is the core problem. To print transistors on a chip, you shine light through a stencil-like mask, and that light burns a pattern into a light-sensitive coating of a silicon wafer. It's essentially photography, just an incomprehensibly small scale. The catch is diffraction. When light passes through a gap smaller than its own wavelength, it spreads and blurs. You cannot print a feature smaller than the wavelength of light you're using without serious engineering gymnastics. For years, the industry used 193 nanometer light from deep ultraviolet lasers. To get around that diffraction limit, chip makers started doing multiple patterning, essentially printing the same layer several times at slightly offset positions and using clever chemistry to combine them. It works, but it multiplies complexity, cost, and the chance of defects. Even then, 193 nanometer light has been wrung dry. The industry needs something fundamentally shorter, and that is what brought ASML to the center of the semiconductor world. You see, ASML is a Dutch company that holds a near total monopoly on extreme ultraviolet lithography machines. There is no real competitor. If you want to make a leading-edge chip, you can go through ASML and nothing else. Their EUV machines use light with a wavelength of just 13.5 nanometers, more than 14 times shorter than the deep ultraviolet light used in older systems. No lamp, no conventional laser produces EUV light naturally. So ASML invented a completely new way to create it. Inside the machine, a generator fires 50,000 microscopic droplets of molten tin per second. Each droplet is about 25 microns across, which is roughly a third the width of a human hair, traveling at 70 meters per second. A first, low-power laser pulse hits each droplet and flattens it into a pancake shape. Then a second, far more powerful CO2 laser blasts the pancake and vaporizes it onto plasma that reaches temperatures of around 220,000 degrees Celsius, which is roughly 40 times hotter than the surface of the sun. That plasma emits EUV light. The light is then collected by a curved mirror and bounced through a series of incredibly precise optics. Mirrors coated in the alternating layers of silicon and molybdenum are just a few atoms thick before being projected through a pattern mask and onto the wafer. UV light is absorbed by almost everything, including air and glass, so the entire interior operates like a vacuum. No glass lenses, just mirrors. The most precisely polished mirrors ever manufactured. The standard EUV machine costs somewhere in the range of $150 to $200 million. The new High-NA version costs around $380 million per unit. Now, standard EUV has been in high volume production since around 2019, and it genuinely changed the game, but as nodes push below 5 nanometers, and certainly below 3 nanometers, even EUV is starting to show cracks. The main issue is stochastic noise. EUV use photons to expose a resist on the wafer, and at these scales, the number of photons hitting any given spot is actually quite small. Photons behave randomly. Small fluctuations in how they land create variations in the edges of the printed features, which is called edge roughness. At 2 nanometers and below, that roughness becomes a real reliability problem. Transistors do not switch cleanly, yields drop, and then there are also defects from the tin plasma process itself. The superheated tin splatter builds up over time on the machine's internal components, which degrades performance and requires expensive maintenance windows. And then there's the power consumption. Running an EUV source is a massive energy-intensive process. The conversion efficiency from laser input to usable EUV output is extremely low, meaning that the machines guzzle electricity just to generate enough light. The industry's answer has been High-NA EUV. The High-NA machine, specifically ASML's TwinScan EXC5000 and the newer EXC5200B, increased the numerical aperture of the optics from 0.33 to 0.50 feet. A higher numerical aperture means sharper focus and finer resolution. High-NA can resolve features down to about 8 nanometers per single exposure compared to 13 nanometers for standard EUV. Intel completed the assembly of the first commercial High-NA EUV machine at its D1X fab in Oregon, and in December 2025 deployed the second generation EXC5200B. But High-NA has its own set of problems. The larger optics require a smaller exposure field per shot, meaning that the machine covers less area per pass. That cuts wafer throughput unless you use more machines, and at $380 million apiece, that adds up fast. Now, this is where DSA comes in, and honestly, I think it might be the most elegant idea in semiconductor manufacturing right now. Traditional lithography is what engineers call a top-down process. You use light to carve patterns into a material, just like a sculptor cutting into stone. DSA flips that model. It's a bottom-up approach where you let chemistry do the patterning for you at the molecular level. The key ingredient here is a class of materials called block copolymers, or BCPs. These are long polymer chains made of 2 chemically distinct segments bonded together. One segment can, for example, be hydrophilic and one hydrophobic, meaning they repel each other. When you coat a surface with these materials and apply heat or a solvent process, the 2 segments spontaneously segregate into incredibly regular alternating patterns. Lines, cylinders, spheres, depending on the chemistry. They self-organize. The pattern emerges from the physics of the molecules themselves. On its own, that self-assembly is random in terms of orientation. This is where the direct part of DSA comes in. You first use EUV lithography to print a rough guiding template on the wafer, a sparse pattern of chemical contrast. Then the block of copolymers align that to the guide and fill in the spaces with features far smaller and sharper than the EUV exposure alone could achieve. The EUV pattern does not need to be perfect, it just needs to be good enough to orient the polymers, and the polymers handle the finer details. In 2024, researchers at Tokyo Institute of Technology and Tokyo Oha Kogyo demonstrated a tailored block copolymer that reliably self-assembled into parallel line patterns with a half pitch of 7.6 nanometers. This is well below what High-NA EUV achieves on its own, and because the critical dimension is set by the polymer chain length, it's tunable. The leading DSA chemical manufacturer has shown 9 nanometer critical dimension with a path towards even smaller. One more thing worth understanding is that DSMA dramatically reduces line edge roughness. The self-assembly process produces extremely clean, regular features regardless of the roughness in the guiding EUV patterns. That directly addresses one of the biggest failure models of EUV at advanced nodes. Now, Intel's 14A node, which sits within the 1.4 nanometer class, is where it all comes together. Intel is combining High-NA EUV with DSA for at least 3 critical layers on the 14A process. This is not just an incremental tweak, it's a fundamentally different manufacturing approach. Intel has essentially gone all in on the High-NA EUV in a way that neither TSMC nor Samsung has. Both have ordered High-NA tools, but only for R&D. Intel is the one pushing for high-volume manufacturing with these machines and ordering multiple ASML High-NA EUV tools and commuting hundreds of millions before the technology was fully proven. The logic makes sense when you look at economics. High-NA single exposure by itself is more expensive than double patterning with standard low-NA EUV. The thought but penalty from the smaller field size is real, but pair High-NA with DSA and the equation changes. DSA can rectify EUV printed guide patterns and define the finest features within a process that is largely self-correcting. You reduce the number of exposures needed, lower defect rates, and improve yield, and Intel has already shown substantial yield improvements on low-pitch metal and via layers by incorporating DSA into the patterning flow. TSMC's competing node, the A14, reportedly will not use High-NA EUV. They have publicly stated that they have no near-term plans to do so. They're scaling their existing low-NA approach further, which is more conservative but also less risky in the short term. Samsung's position is similar. Intel's bet here is enormous. 2 High-NA EUV machines for high-volume manufacturing costs and around $760 million in just the tool procurement. The company has said it may cancel the 14A node entirely if it cannot win a major external customer to justify the capital outlay. This is how high the stakes are, and honestly, I'm here for it because this is the first time in decades that we've seen a rivalry so good and so productive as this one.